RAM. RAM stands for Random Access Memory, and it is the main working memory of your computer. Every time you open a program, load a file, or switch between browser tabs, that data gets loaded into RAM so the processor can access it quickly. RAM is volatile, which means everything stored in it disappears the moment you turn off your computer. The random access part means the processor can jump to any piece of data in RAM equally fast, no matter where it is located. Older storage methods, like magnetic tape, had to be read in order from start to finish. RAM does not have that limitation. The RAM sticks on your motherboard are almost always a type called DRAM. The other main type is SRAM, and it serves a very different purpose. DRAM. DRAM stands for Dynamic Random Access Memory, and it is the type used as main memory in almost every computer, laptop, phone, and game console. When people say my computer has 16 gigabytes of RAM, they are talking about DRAM. Each bit of data in DRAM is stored using one capacitor and one transistor. The capacitor holds a small electrical charge representing either a 1 or a 0. The problem is that capacitors leak charge over time, so the data fades unless each cell is refreshed roughly every 64 milliseconds. That constant refreshing is what makes it dynamic. This simple design makes DRAM very dense and cheap to produce, but slower than SRAM because of the time spent refreshing. The DDR4 and DDR5 sticks you buy today are modern generations of DRAM. SRAM. SRAM stands for Static Random Access Memory. Unlike DRAM, it does not use capacitors. Instead, each bit is stored using a small circuit called a flip-flop, made up of 4 to 6 transistors. Because there are no capacitors leaking charge, SRAM does not need constant refreshing. That is what makes it static. SRAM is significantly faster than DRAM, but 4 to 6 transistors per bit means it takes up much more space and costs far more to manufacture. Because of that, SRAM is never used as main memory. It is used where speed matters more than capacity, most importantly inside the processor itself. Cache memory. Cache memory is a small amount of very fast SRAM built into or right next to your CPU. It stores the data the processor is most likely to need next, so it does not have to wait for the much slower main RAM. Modern processors have 3 levels. L1 is the smallest and fastest, sitting inside each CPU core, typically 32 to 128 kilobytes. L2 is larger, usually 256 kilobytes to 2 megabytes per core, but slower. L3 is the largest, often 16 to 64 megabytes or more, and unlike L1 and L2, it is shared across all cores. When the CPU needs data, it checks L1 first, then L2, then L3. Finding the data in cache is called a cache hit. If the data is not in any cache, the processor goes to the main RAM, which is much slower. That is called a cache miss. Registers. Registers are the fastest and smallest memory in any computer. They are not a separate chip. They are tiny storage locations built directly into the processor, right next to the circuits that do the actual computing. A register holds the exact piece of data the CPU is working on at that very moment. When the processor adds 2 numbers, those numbers are in registers. Registers are measured in bits, not megabytes. A modern 64-bit processor has only around 16 to 32 general-purpose registers, each 64 bits wide. The full memory hierarchy flows like this. Data is stored long-term on a drive, loaded into RAM when needed, pulled into cache, and finally placed into a register right before the CPU processes it. VRAM. VRAM stands for Video Random Access Memory, and it is the dedicated memory on your graphics card. While regular RAM serves the CPU, VRAM serves the GPU, the processor responsible for rendering everything you see on your screen. VRAM stores textures, frame buffers, and 3D model data. Having this memory separate from system RAM means the GPU can access its data without competing with the CPU for bandwidth. Modern VRAM uses GDDR, which stands for Graphics Double Data Rate. It is based on DRAM technology but redesigned to prioritize bandwidth, moving large amounts of data at once, which is what GPUs need most. Unlike system RAM, VRAM is soldered onto the graphics card and cannot be upgraded separately. Computers without a dedicated graphics card use an integrated GPU, which shares system RAM instead. Virtual memory. Virtual memory is not a physical chip. It is a system managed by the operating system that uses part of your storage drive as if it were extra RAM. When your RAM fills up, the operating system moves the least recently used data to a special file on your drive, called a page file on Windows, or a swap file on Linux. When a program needs that data again, it gets swapped back into RAM. This lets the computer handle more tasks than its physical RAM could support on its own. The trade-off is speed. Even the fastest SSD is dramatically slower than RAM. Heavy reliance on virtual memory causes noticeable slowdowns. The best fix is adding more physical RAM so the system does not need to swap as often. ROM. ROM stands for read-only memory. Unlike RAM, ROM is non-volatile. It keeps its data even when the computer is powered off. It was designed to store permanent instructions a device needs every time it starts up. Traditional ROM is programmed during manufacturing and cannot be altered afterward. Pure, unchangeable ROM is rare in modern devices because the need to update firmware led to more flexible versions: PROM, EPROM, EEPROM, and flash memory, each making it progressively easier to erase and rewrite stored data. PROM stands for Programmable Read-Only Memory. Unlike basic ROM, it can be programmed after manufacturing, but only once. Inside a PROM chip, there are tiny fuses, one for each bit. Programming means burning specific fuses using a PROM programmer. Once a fuse is burned, it cannot be restored. If a mistake is made, the chip is discarded. For this reason, PROM is also called OTP, one-time programmable. That inability to correct errors led to the development of EEPROM. EEPROM stands for Erasable Programmable Read-Only Memory, and it solved the biggest problem with PROM, the fact that you could not erase it. An EEPROM chip can be erased and reprogrammed, but the process is unusual. You expose the chip to strong ultraviolet light for about 15 to 20 minutes through a small quartz crystal window built into the top of the chip. The UV light clears the stored charges, resetting the chip to a blank state so it can be reprogrammed. During normal use, the window is covered with a sticker to prevent accidental erasure. EEPROM was a big improvement, but the slow process and need to physically remove the chip drove the development of EEPROM. EEPROM stands for Electrically Erasable Programmable Read-Only Memory. Instead of ultraviolet light, EEPROM can be erased and rewritten using electrical signals while the chip is still installed in the device. Another improvement is precision. EEPROM erases the entire chip at once. EEPROM lets you erase and rewrite individual bytes without touching the rest. EEPROM is used to store small amounts of data that need to survive a power loss, but also need occasional updates. Things like BIOS settings on a motherboard or firmware in car key fobs. Its main limitations are speed and cost. It is slower and more expensive per bit than flash memory. Flash memory is a direct descendant of EEPROM. It uses the same basic principle, storing data as electrical charges, but engineered to be faster, denser, and cheaper. The key difference is that EEPROM erases 1 byte at a time, while flash erases in large blocks, making it much faster for handling large amounts of data. There are 2 main types. NAND flash is the most common, used in SSDs, USB drives, SD cards, and phones. NOR flash is mostly used for firmware because it allows code to run directly from the chip. Flash is non-volatile, has no moving parts, and is more durable than traditional hard drives. The full ROM family evolution goes ROM to PROM, to EEPROM, to EEPROM, to flash, each step making it easier and faster to erase and rewrite data.